Today's topic of discussion is what attributes of an injection zone serve to contain reinjected produced water. And we have three very distinguished speakers. We don't have enough time to go over every single bio, but I will just introduce them very quickly before I hand it off. Our first guest speaker is Dario Stenberger. He's the Vice President of Engineering with NSI Technologies. Our second guest speaker, who really doesn't need an introduction, is Dr. Michael Smith. Michael Smith is our president, or currently our CEO, and also a founder of NSI Technologies. That S stands for Smith in NSI. And our third speaker is Dr. Abhijit Mitra, who is a senior geomechanics advisor with Premier Corex. So without further ado, welcome, Dario, and I'll stop sharing my screen and I'll let you take over from this point.
All right, hopefully you can see my screen and you can hear me.
I can. Just do not see your video yet, but that's screen and audio looks great.
Okay, so you don't see my presentation yet?
I see your presentation, just not your video camera.
Okay, hang on. Let's there we go. Okay, sorry about that. Well, good morning, everyone. So this was a presentation that we were asked to put together for the Texas Railroad Commission, and they wanted us to have a look at some of the issues they're having with injection of produced water. So we're going to have a look at some case histories, and I'll look at we'll tell you what the purpose of the whole thing was first. I'm going to read these because they're sort of important as to how we develop the presentation and what we're going to talk about. So we want to talk about the potential issues with long-term water disposal in wells. Mike's going to present a couple of stories to illustrate that this is not a new phenomenon, but that industry does have the experience and the tools to prevent these potential problems. We'll have a review of rock mechanics, reservoir changes due to long-term injection. We'll show what laboratory testing is required. We'll touch on field monitoring, and we'll show some modeling that can be performed using the laboratory tests and some of that field data. And then we'll have a discussion at the end. So the agenda is a little different in that we're going to start with case histories and then go into the actual meat of what we need in there. So Dr. Mike Smith will talk for a few minutes, myself, and then Abhijit will follow that. So with that, I'm going to hand over the mic to Mike and let you at it, Mike.
Okay, thank you, Dario, Dante. You know, there's a very old song by Marty Robbins, The Ballad of the Alamo, and one of the stanzas begins with, let the old men tell their stories. So these are a couple of anecdotal experiences from long ago. The first one was in West Texas in the Level Land Unit, a very large water flood operated by Amoco. This is when I was with Amoco Research Center. And I had been loaned to the Level Land Unit as they were looking at transitioning from acid frac to prop fracs, and they asked for some support from the research center. But in the area where we were working, the offset operator across the lease line was injecting at much higher pressures and rates than we were, and had a line of injectors right along the boundary. And so we were converting some injectors producers and drilling some new wells, thinking, well, probably they're pushing some oil our way with these higher injection rates. So the drillers were drilling a new well in that area, and at some shallow depth, I don't recall where, but thousands of feet above the reservoir, they had what they termed a cold water blowout. And they fought this for several days and could not get it under control. Finally, they asked the offset operator to shut in 3 or 4 injection wells, and that allowed them to finally get this under control. And so they abandoned the well and gave up drilling any wells in that area. Basically, their injection at well above frac pressure had supercharged formations thousands of feet above the pay zone. The second example, a little bit newer, but still quite a ways back. I came to know this. I was on a technical advisory committee for the management of a North Sea operator. And the subject of injection had come up in this one field because there was not a lot of barrier above the pay zone because of geologic features. And so containment of the injection was a bit of concern. And, you know, I noted that, well, we started out injecting below frac pressure, but because of thermal effects, cooling, we were undoubtedly above frac pressure now, injecting cold North Sea water into the reservoir. But I opined that that was a good thing, that the cooling of the reservoir would reduce frac pressure there and aid in containment. It turned out, I guess I was wrong. Some years later, and I was no longer involved in this, they were doing an ROV camera inspection of the platform legs, and they accidentally turned the camera around and discovered a mini volcano on the seabed where the injection had breached the surface of the seabed. I know there was a big study done on this. Amazingly, it never was published or became public in any way. There's nothing on the internet about it. I do remember that the final breach to the surface involved a fault. But beyond that, I don't know any of the details of what they discovered about this. But again, shutting in the injection did shut off the volcano. So just a couple of anecdotal stories of where containment has been lost due to subsurface water injection. And with that, I will turn it back over to Dario and Abhijit.
All right, thanks, Mike. Come on. There we go. So I'm going to look at some modeling studies, and the simulation that I'm going to show you was really done before any injection was done in the field as part of a containment study, and it was just to learn what the long-term effects of injecting produced water would provide. So one of the fundamental things we have to look at is the Eaton equation. Even though that was derived to determine pore pressure, we can rearrange that. And most of us have seen this equation before, where you've got Young's modulus, Poisson's ratio, overburden pressure, Biot's coefficient, and reservoir pressure. Many of us also know that there's a tectonic factor that can be taken into account where there's faulting or in mountainous regions, especially up in the Rockies. What most of us don't really ever see in this equation or realize is that there is this thermal effect that Mike was talking about, and that the stresses change with that injection water. But what we'll see is that the change of that is far less than the change due to the injection pressure. So there's a definition here. I think most of the audience is familiar with these terms, and squish over squash for Poisson's ratio, and the change or the force over the change in diameter and length for Young's modulus. And these are all important things to understand at day one before we start injection, and then how do these things change as we start injecting. None of these terms are constant. Biot's coefficient, pressure, none of this is constant through the life of injection. They're changing, and these are things we can look at in a laboratory setting to help us in the modeling and understanding what's happening. So one of the best ways in my 38-year career has been to look at models and just see what iterations and how differences in that model can change the outcomes. So this is another busy slide, but the middle of it here is really what we're setting up. In blue here, there's some pore pressure, original pore pressure. We have in green the original minimum horizontal stress. Typically in a normal stressed environment, the minimum horizontal stress will be higher than the overburden, or sorry, the pore pressure, and then you've got your overburden. As we start injecting, the pore pressure will increase, the minimum horizontal stress will increase, and at some point in time, because you're in a contained environment, you will exceed the stress in this formation and possibly break through your seal. And that's what we want to look at in terms of long-term injection. So to set up a model, there's various things we need. First, what do you need for a reservoir? Well, you need something that's got high permeability, preferably not hydrocarbon bearing, or it's been, you know, depleted of hydrocarbons, but you have really high permeability. So in this case, in this scenario, we've got 1 to 8 Darcy's of permeability. We've got a large perforated interval. We're going to be injecting at a high rate, 24 barrels a minute, for the life of this injection well over a period of 25 years. And you need your standard reservoir data to plug into the model. So in the next 3 slides after this one, I'll show you just some simulation loops and what they look like with that injection, just to familiarize yourself with those plots that are coming up. You'll see this sort of color pattern here. That's the perforated interval. The yellow are our high permeability streaks, 1 to 8 Darcy's. This black line here is the minimum horizontal stress at day 1. So at the start of injection, you'll see some sort of injection profile. You'll have a time up here, and then there'll be various graphics that will be showing from width and stress, etc. So just to set up the case. So this is just a loop. You'll see time increasing here in each of these blocks. On the left, this is the width of the injection zone. We'll let this loop through again. On the right, we'll see the temperature changes with injection, cooler temperatures in blues, hotter temperatures, or the reservoir temperature in this case in the pinks. This pink outline is the actual fluid injection front. And you'll see when this loops around again that up until about 57 months, we stay within the injection zone. And then when this hits about 57 months, we start breaking through the seal. We've got 2 of them here, and we've broken through, which means we've lost upper containment of the injection. We don't have any data above here, but we don't want to break through this seal, and that was the point of this simulation. So on this next slide, now we're going to look at the poroelastic and temperature changes during the injection. So it's the same time scale, same everything, except the colors that we're showing. In this case, we're looking at the stress change with time, and on the right, we're looking at the stress change with temperature. So as we increase pressure, we're going to see a positive stress increase. As we cool the reservoir, we'll see a negative stress increase, but we'll see that, again, we've broken through and breached the seal of our rock here. So the final simulation that I'm going to show you is the overall stress change in the reservoir. So you'll see that there are stress changes from day 1 when we start injecting in the overlying and the layers below us. The pink again is the fluid front. Everything ahead of it, above and below, are the stress changes with time. And we'll again see that about 57 months, you'll see this pink line breaks through that. and we've broken through our seal. And this is what we want to prevent. So we need to know how that Eaton's equation changes that stress with time. And the original, all of the original properties of the formation are changing with every time step, with every injection. So that's the quick modeling update. And with that, I'm going to turn it over to Abhijit. So if you would get your mic on and your camera.
Yeah, thank you, Dario. I hope you can everyone can hear me and also see my video. What I'll be doing here is I'll be just providing some basics of the geomechanics and try to explain some of the fundamentals behind the parameters that Dario showed just a few minutes back. So the geomechanics plays a critical role wherever we are into the produced water injection, because the in situ stress, the pore pressure, and the strength of the rock, both the tensile and compressive, all of them play a key role. Then we also have to consider about brittleness or ductility of the subsurface formations. And finally, there is something else also that we call the coupled processes, but we will not be talking about those in this presentation due to the time limitation. So next slide, please. I mean, most of us already know the overburden stress is nothing but the weight of the overlying column of the rock. And then depending on where the formation is located, if it is near to a mountainous region or near to any fault, then our two in situ horizontal stress component, the SH mean and SH max, can be different. There will be stress and isotropy. But not only that, the subsurface actually has all of these pores that created during all these depositional and diagenetic processes, and they contain oil, they may contain gas, and of course, whenever we are injecting produced water, they will contain the water in there, and that will actually create a pore pressure. So effectively, the individual grains or the matrix of the formation there will see something of what we call an effective stress, which is actually a difference between the overburden or the applied stress and the pore pressure times the poroelastic or the Biot's coefficient. We need to actually know the effective stress of the formation, because if you, next slide, please. Like I'm showing you here, the stress state of the formation at any particular depth or any particular point in the failure envelope. So depending on how the order of the magnitude for the overburden and the horizontal stresses, it can be any kind of stress regime we may have. But since we are actually using effective stress instead of the total stress to display in this kind of graphic, so whenever we are actually injecting in the subsurface, the pore pressure increases, and that leads to a drop in the effective stress. So whatever stress state or the stress regime you are in, the circle will actually move towards the left and move closer and closer to the failure envelope that is shown in this red straight line. And whenever they are in contact, that's when we will see things like wellbore integrity loss and of course we will see that's when we will have the caprock breaching and things like that. So that is why we actually perform elaborate geomechanics modeling. And if I go to next slide, we can actually have these geomodels either for the entire basin or for the part of a basin, and definitely we can just center it for the well of interest for sure. And the one important thing, next please, the one important thing we actually have to remember whenever we are building this kind of geomodel is this is a little different from our conventional geomodel that we build for the ENP operation, because we not only have to characterize or model the reservoir interval, but we also have to we also have to think about the cap rock because we need to know the rock mechanics and as well as some of the petrophysical properties like the capillary pressure and wettability and so on. Next, please. There is multiple ways to build the geomodel, but most often we end up using this phases-based approach, and the phases can be a fit for purpose and can be built by incorporating all the geological reservoir and in some cases, like for the ENP cases, also the completions data, we can bring all of them together. And for example, the geomodel that I'm showing you here, we are actually looking at different production quality phases in. And if you kind of see that along each of these laterals, we are actually seeing this heterogeneous distribution of these production quality phases. So we can actually build the phases model or the geo model that has all the phases impregnated to it in such detail that it will actually help us to even model the produced water reinjection. Next slide, please. This is an example of a geomechanics model that has the phases that we put them in the order of increasing brittleness, with 1 being the most ductile and 8 being the most brittle phases. And also we have the V-line model also shown here as a reference. Next slide. So I just wanted to take a little bit of time to show you how we build this kind of geomechanics model. We start with the 1D where we have the sonic log and the density log data, and then whenever we do perform the rock mechanics measurement in the laboratory, we bring those data in as well. And then we actually measure the static and the dynamic mechanical properties, and I will also tell you how to do that very soon. But then once we have those properties, we kind of try to build a set of correlations, which finally kind of gives us to the input to all the parameters necessary for the Eaton's equation that Dario showed before, and that kind of completes the horizontal stress profile, which is like a kind of like a key to this modeling exercise. Now, very quickly, let's look at this case study that was published in SPE ATC 2 years back for a field from the Kuwait. Again, we started with the sonic data, and next slide, please. We are actually showing you some of these transform or the correlations that we can actually build using the laboratory measurement. For example, the one in the top middle that is actually plotting the P-wave velocity measured at parallel to bedding as a function of P-wave velocity measured perpendicular to bedding. And on the bottom right, we are actually showing you the famous dynamic to static transform. So once we have all of these transformed, then next slide. We actually obtain these pseudo velocity logs. For example, if you go to the extreme right, the VP90 pseudo log and the VS90 pseudo log. This is something that our sonic tool does not give us, but using the correlations that we just obtained from the lab measurement, we can actually obtain this sort of logs. And then once we have everything, then if you go to next, we can generate these static anisotropic mechanical properties like the vertical and the horizontal Young's modulus, Poisson ratio, using like well-published rock physics equations. And finally, we also measure the Beard poroelastic coefficient, and we can actually have this sort of pseudolog for the Beard coefficient as well. And it always helps to have something like a defeat data or things like that. But if we don't have, we still have some internal checks or validation exercise to run. For example, in the next slide, what we have done here is we actually plotted the P-wave velocity as a function of the elastic anisotropy expressed as the ratio between the Young's modulus perpendicular and the parallel to bedding. So what we see here, if the sonic velocity is extremely high, the anisotropy is extremely low, and vice versa. And not only that, the very high sonic velocity is accompanied by the low clay and the high carbonated content, whereas where we have the very high anisotropy, we have extremely high clay content but very low carbonate content. So this is one of the ways things that we can do. Next slide, please. So the geomechanics measurement that we need to run mostly is that we call the triaxial compressive strength test. So what we do here is we actually apply and hold constant stress, which we call which can be equal to the net confining stress, and then we apply the axial load shown by those pink arrows at a predetermined rate till the sample fails. And during this entire process, we can actually monitor the change in sample length and sample diameter, which will actually help us to estimate the Young's modulus and the Poisson ratio, which we actually call, those are our static mechanical property. Now, if we go to the next slide, I will, so this cartoon on the left kind of tells you, because we know our caprock, these are mostly anisotropic, and we use the TIV anisotropic model. So we actually take one plug perpendicular to the lamination and the other one parallel to the lamination to complete the, to conduct our triaxial compressive strength measurement. And on the right, I mean, this is just, I mean, you can ignore, but some of you already know, this is the anisotropic stiffness tensor. So this is where we actually have the EH and EV, that is the Young's modulus perpendicular and the parallel to the bedding kind of comes into play, and that's what we try to estimate. In the next slide, I'm actually showing you the experimental setup. So the sample sits in the middle between two end caps, and each of these end caps actually houses few piezoelectric transducers, which has the ability to send and receive ultrasonic velocity signals, and they are actually of frequency close to the megahertz. And in compared to, if you think about it, your sonic tool actually has a high kilohertz frequency. So we actually can transmit one compressional and two shear wave velocity through the plug sample whenever we are running the triaxial test. And then we also have our that we call the deformation transducers to monitor the change in sample length and sample diameter. Now, if we go to next slide, since we have two shear wave velocity, so whenever we are actually taking a plug sample that has been drilled parallel to the bedding, we will actually see shear wave splitting, which is like, if you go to the bottom right, you will see that there is a fast shear and the slow shear, which we will not see if the sample actually has been drilled perpendicular to the bedding, because that's what the principle of the theory of the transversal isotropy tells us. So from these, all this velocity that we are measuring, we will then again use the principles of rock physics to calculate the dynamic mechanical property. So that gives us the static and dynamic mechanical property. Now, next slide, please. Some example data from the Permian Basin. So for example, on the left, we are showing you the bedding perpendicular and the bedding parallel Young's modulus, with bedding parallel is always higher than the bedding perpendicular one. And in the right, we are looking into some of the static to dynamic transform. And you will see that we actually have two separate transforms for the two different orientation, perpendicular and the parallel to bedding. Next slide. Changing gears a little bit here to talk about the brittleness. We all know glass is brittle because when glass breaks, glass shatters. But if you try to do the same thing with a Play-Doh, it will not shatter. So rock can be something in between a brittle and ductile, and that kind of depends on its mineralogical makeup, in situ pore pressure, the temperature at which the rock is, and finally the applied NCS. So if you go to the next slide, on the left, I'm actually showing you this example from the literature. So he is actually, this gentleman is reporting a series of triaxial compressive strength tests. So whenever he applied like a very low confined NCS, say for example, a 0 megapascal, he found a brittle failure. And as he continually increased the applied NCS from 5 to 20 or 30 megapascal, we are looking at something that we call the brittle to ductile transition. And finally, at a very high NCS, we are actually seeing a ductile, completely ductile behavior. And since this, whether the rock behaves brittle or ductile kind of has a role to play in how the caprock will fail if it fails, in the event of it fails. So that is why, like Dario was explaining, we need to actually estimate the mechanical property of the rock, the failure behavior of the rock at the different timestamp. Because with continued injection, the pore pressure gradient will change. And with that, the applied stress will change and everything will change. So that is why we actually need to build a dynamic geomechanics model for each of these uh, steps during the injection, say after 3 months, after 6 months, 1 year, 5 year, 10 year, and whatever you want it to be. Very quickly in the next slide, I'm just telling you how we actually move from the 1D to 3D geomechanics reality. So we start with this calibrated 1D geomechanics model. And if there is any gap in the data that we feel that it should not be, we take help of something like an artificial neural network to fill in those gaps. And then we also need to build a static geomodel, and we'll import the 3D grid from that. And we'll put them together. And the next step will be actually obtaining the phases that which can be production quality phases, it can be phases based on brittleness, and we will put all of them together to have this 3D phases model, and that will kind of finally turns into the 3D geomechanics model. And in the next slide, which will be the last slide of my talk, I'm again kind of coming back to the example that Dario showed before. We are looking at the different pore pressure, 3 different pore pressure gradient that we will see during the injection. And for each of them, we are from the dynamic geomechanics model, we will actually get different minimum horizontal stress. So obviously, you can understand by now that like the purpose of this geomechanics modeling exercise will be nothing but to give Dario to have all his inputs so that he can actually perform his simulations and tell you if the caprock is going to breach or not, and if it breaches, when will it breach. So with that, I kind of stop talking and get it back to Q&A. Thank you, everyone.
All right, Dante, take it away.
Very good. Well, thank you very much, gentlemen, for an excellent talk. We're a little early on time, but that means we have more time for Q&A. So there is one comment here by Robert Bachman, but it is a little off topic. It's about Canada, and he's saying energy regulators in Canada license maximum injection pressure into formations for either water, steam, or CCUS. These typically are a fraction of the initial closure stress. These are also continuous monitoring requirements. What are the current regulations in Texas and other states, and what tests need to be run?
That's a great question. This is not something that we discussed with the Railroad Commission. I think they have some guidelines, but I don't know that they have legislation per se like they do in Canada. I remember in Canada they used to make all the operators do yearly build-up tests on their gas wells. I've never heard of that down here in the States, so I don't think the legislation is anywhere near as stringent as it is up in Canada. And I think that's the reason the chief engineer asked for this kind of a talk, because I don't think you can just set a set of criteria today and leave it at that. I think things change with time. What we didn't talk about was formation damage and how injectivity through time will actually reduce because of carryover of chemicals, fines, etc. And so if your injectivity is going down, but you still have the same criteria for injection pressure, and you could be in a world of hurt. And I think that's what they're looking at and trying to prevent.
That's a very good point, Dario. And you actually bring up a whole topic of discussion here that could be a topic in its own, but the concept of the injectivity changing with respect to time and also with respect to temperature and the type of total dissolved solids in the injection fluid versus any potential reactions in the connate fluid in the injection zone. So I guess the question I'd like to bring up mainly for Abhijit is, in addition to geomechanical tests, do you perform these long-term injectivity tests or formation damage tests at various injection pressures and different temperatures? Or what would be a recommended set of tests to determine this long-term injectivity into disposal zones?
I'm sure there will be a number of tests that we can actually perform while trying to look into the injection-induced formation damage. However, the problem is there are a number of tests that we can actually do into the formation damage to evaluate the formation damage, and it is sometimes not very easy to comment for a person like me who is actually not a formation damage expert. But one thing I can actually tell you, and this was a conversation I had with one of an academic partner a few weeks back, that they wanted to see. So, for example, whenever we look into a reservoir that is actually an unconsolidated sand reservoir, we have this. There is a potential of having sanding issue, and we actually run something called a thick wall cylinder test, where we kind of like increase the applied NCS on the sample till the sample, which is actually a form of a bored tunnel, kind of collapses. So he was wondering that if we can actually do that test, but in reverse. So instead of increasing, instead of trying to mimic the drawdown, if we can actually mimic the injection on that. So there is obviously ways to do that, but that is all kind of still into me or some other, like some people who are like the geomechanics expert or the lab geomechanics expert. So that is still kind of in someone's head. I think we still need to spend some effort to actually bring it into a drawing board and finally into a lab bench. So I guess that's what my reply will be.
Thank you for that expanded commentary, Abhijit. There's another question here from the audience. It's a little lengthy, so let me read it through. It's from William Harbert, and he's asking, when you add fractures to the system, things get even more complicated, which is very correct. With respect to the North Sea examples, how can the rock physics presented be modified to include these fracture systems? Another question, do you feel that reactive geochemical changes are also possibly relevant to brittleness? Last question, do you have basin-specific formulas for the dynamic to static moduli equations? So I guess we'll go one by one. These are three very different questions. The first is, how do you account for the fractured reservoir system? Do you basically treat it as a system perm or a system mechanical properties? What is your recommended policy or recommended procedure to account for the fractures in the system?
Mike?
Yeah, that's an excellent question. The only way, I would know to account for it in any of the models we have would be as a system permeability. The North Sea case, I was not privy to the study that was done, but I do know that a fault was a big part of it, actually bringing the injection fluids to the surface or to the seabed did involve a fault. How that was modeled, I don't know, but it was modeled as a single fault, not a fracture system. In terms of just general injection, I think it would be treated as a permeability, although it would probably have to be an anisotropic permeability. That is, you'd get a preferred direction of injection along the primary direction of the natural fractures. But that's about all I can think of to add.
I think that's correct, Mike. Definitely the anisotropic model would be the most suited, like you said, with the preferential directions. The part 2 question from the same participant in the audience is, do you feel that reactive geochemical changes are also possibly relevant to brittleness? So I do know, and Abhijit, you described this, the Moore-Coulomb failure criteria and the effective confining stress affects the rock strength as you change the pore pressure in the system. But when we have this formation damage, chemical deposition, or geochemical changes, would that have any possibility to affect the actual mechanical properties of the rock itself? Or, I don't know, how do you address this question?
Dante, if you remember, when I first started talking in my very first slide, I showed that coupled processes do impact the produced water injection, but I will not be talking about it because it is actually a topic of its own, and also a topic where we actually don't know a lot right now. So, for example, I can tell that I think that's from a scientist at the Lawrence Berkeley National Lab. They actually have this simulator called Tough React that can actually perform geochemical simulation for these scenarios. But then, of course, whenever you are running these sort of simulations, you need to have some data to ground truth the simulation results. So we are actually talking with some of our overseas partner because there was somewhat like an R&D kind of project came up related to, I think it was regarding CCS. So there, what we are going to do is we are actually taking some of these rock samples and we will actually age them in some sort of reactive fluid for different time duration. And then we are going to run these triaxial compressive strength tests. And one thing that I have not done in my presentation is I have not actually shown an output of triaxial compressive strength test, which is the stress strain plot. So in the stress strain plot, if we actually allow the test to continue even after the failure, so the post-failure behavior from the stress strain plot kind of tells you about this sort of the brittleness behavior, whether we are going to see brittleness or not. And this is something we actually just did for a very large engineering firm in US for a CCS site. So that is something we can definitely do. And we're actually going to do it for someone. So we can do that. And while I am at it, I guess I will also answer this question on the basin specific formula. So yes, we do have basin specific dynamic to static transforms, but more often than not, we found that a basin, which is kind of like a very, very large area, and that can be split into all these different horizons. For example, just look into Midland Basin, we have the Wolfcamp A, B, C, there is this ash bed, there is this there is an alternate carbonate sequence, and all of this formation, if we have sufficient data point, we can actually have a separate transform for each of these different formations. So it can be very interesting, and sometimes I think we will be doing an injustice if we are just use some general transform for that is applicable for the entire basin instead of these different formation specific transforms.
Very good. Thank you for that explanation, Abhijit. That makes a lot of sense. I'm going to skip over some of the questions, and then if we have time, come back to them. But I want to bring up one question that I think is very interesting from Marat Kozbarmokov. And he's asking, are there any recommendations for executing a propped fracture for long-term injection wells? I do know, for instance, in our model, StimPlan, we have a coupled model that couples our fracture propagation module with the reservoir simulation component. to ensure that when we're injecting into saltwater or wastewater disposal wells, we're not exceeding the fracture gradient. But in the event, I believe the question here is if we could execute a controlled hydraulic fracture where we know we can contain the frac height in the injection zone, we increase the surface area, we have proppant there. So in effect, we're increasing the injectivity for that well and making it a significantly better injector. Is this something that is commonly applied or something that we recommended? And I open the question to Mike, Dario.
Mike, you want to take that? I've got some thoughts on it, but.
Yeah, I don't know how commonly applied it is, but it is definitely done. The one requirement is that you use a very strong resin-coated proppant, or you strictly maintain your injection pressure below the frac pressure. Many years ago, we were doing an EOR pilot in Wyoming, very 2-acre pilot or something. And we couldn't stand to inject above frac pressure, but the injectivity was quite low. So we did some little micro hydraulic prop fracture treatments and really increased the injectivity, and everything was great. But someone came along and returned the injection back to their old rates, which was above frac pressure, and straight away washed away our fracs. When they dropped the pressure again, the injectivity was gone. My daughter was hoping to do a Wednesday presentation on some water injection fracs they did in the Gulf of Mexico using a super strong resin-coated proppant to try to ensure they didn't accidentally wash away the frac. But I don't believe she ever got permission to do that. So yes, prop fracs can be used in injection wells to improve the injectivity, but you'd have to do some extra considerations about post-frac injection behavior.
And one of the things that we've also looked at is skin damage frac. So, your injectivity drops through time, and then go in and do a small frac just to get rid of the damage, because a lot of times we don't know what the formation damage is caused by, or is there a chemical treatment to fix that? Well, a small prop frac could certainly help with that near wellbore. So we've done that before.
Right, very true. Very good point, Dario. And I do want to bring up, since we're on the topic of fracturing on injection wells, Carl Montgomery made a very good comment here in the chat, and he said, despite field rules prohibiting fracturing, every water injector I have ever looked at has been fractured because of long-term cooling. In Alaska, we used to stimulate the water injectors by injecting cold seawater. Do the current Railroad Commission water injection well rules include thermal cooling or back pressure stress change evaluations?
I'm not up to date on Railroad Commission, but I don't think I have ever seen any regulatory requirements that address cooling or back stress, poroelastic effects on fracture pressure. Amoco's policy long ago was to inject below frac pressure, so we would run a step rate test in every injection well every year. We modified that to maintaining a bottom hole injection pressure less than the stress of the shale. And that significantly increased our injectivity, but we still maintain containment because we tried very hard to keep an ejection withdrawal ratio of around 1. But there were no thermal effects because we were primarily injecting produced water. So the injected water was pretty much at the temperature of the formation, but with cooling effects would, as seen in that Narcia case, invalidate that idea of injecting below the stress of the shale.
Yeah. There's a quick comment from Robert Bachman related to Canadian regulations, and he's saying thermal cooling is not a part of the Canadian regulations. One next comment is from Martin Rylance. And Martin is saying, always risks associated with increasing pore pressure above the original charge pressure. Original pore pressure can often be an indicator of seal capability. So depletion, an important part of all these considerations. Very, very well said, Martin. And we do have time for one last question. So I'm going to refer to a little comment here from David Sircone. And David is saying about 12 years ago, produced water injection in Youngstown, Ohio caused earthquakes. And I believe he's saying 3 to 4 magnitude. My observations of the field data caused me to posit that anonymously high injection pressure at the wells compared with that of the region, coupled with suddenly stopping injection over the Christmas holiday, may have caused these events. Any thoughts on this situation? Mike, Dario, do you think the higher than normal injection pressure could have, and the relaxation of that injection pressure over the stopping of the pumping, that cycling of the pressures could have maybe induced a slippage in a nearby fault, or the injection itself could have potentially reduced the friction coefficient on faults in the nearby region, triggering these earthquakes? That's just my initial intuition, but I'll let you comment on what you think might have caused this.
Well, injection can increase the pore pressure and increase the stress, and so that can lead to high injection pressures. With a little plug-in, you have to go above frac pressure. That raising the reservoir pressure raises the frac pressure, so you can get anomalously high injection pressure. So that could certainly cause slippage. I'm not sure how shutting in would affect that. I can't see how the shut-in would affect it, but I can't rule it out. I don't know.
Potentially that buildup of shear in an existing fault from the injection, and then when you shut in, it could have released some of that stress, and the stored energy got released from a slippage event. But I'm just completely guessing here.
Yeah. But I mean, Abhijit showed the more Coulomb envelope you increase pore pressure, you reduce the effective stress on faults. And as we saw in Oklahoma, when the Mississippi line water injection was going strong, we created all kinds of earthquakes where they were injecting into a very low pressure, highly tectonically stressed formation. And so injection can absolutely create earthquakes.
Absolutely. All the more reason why studies of this nature are very important to be conducted, from studying the geomechanics of the reservoir target or the target injection zone, to performing modeling studies and analyzing the geophysics of the area, including 3D seismic, etc., is crucial and critical for the proper evaluation of these injection zones to avoid such issues. But gentlemen, we are out of time for the Q&A portion. I do want to thank you very much, Dario, Dr. Smith, and Dr. Mitra. Thank you very much for sharing this excellent presentation with our audience and for answering a lot of the questions from our participants. And also thank you from all of the participants who participated with the Q&A today with our authors. Your participation is always appreciated and greatly enhances our live sessions. Before you all leave, just some very quick reminders. Next week, we're hosting Robert Hawks, Vice President of Operations with Pressure Diagnostics, and Robert is going to be sharing DFIT best practices and interpretation update with focus on DFIT flowback. So please be sure to join us next week for what I am very sure is going to be a highly technical, highly educational, but very interesting presentation as well. So for all of you out there in the DFIT world and potentially DFIT flowback or completions or even caprock integrity analysis, all of this is very relevant, and I highly encourage you to participate in next week's talk. With that, again, thank you very much to our speakers today. It was a pleasure hosting you, and thank you so much for all the participants who shared the questions and comments in the chat. These sessions would not be possible without your ongoing support, and we really do appreciate it. And lastly, if any of you have a topic or a case study or any type of work that you'd like to showcase on NSI Days, we are always looking for new guest speakers. Filling the sessions weekly is not an easy task. So the more speakers that contact us with interesting topics and case studies, the easier it makes us to be able to maintain these sessions weekly. So if you are interested in sharing a presentation, simply contact us at info@nsitech.com. That's the email at the bottom of your screen. If another way to contact us is by following us on LinkedIn. Simply search for NSI Technologies LinkedIn page and follow us there. You will see constant updates of upcoming NSI Day sessions. You can message us on LinkedIn, or you can also connect with us on our website. There is a way to contact us on nsitech.com. Although the easiest, most efficient is to just shoot us an email at info@nsitech.com. With that, thank you very much, and I hope everyone has a great rest of your Wednesday, and I look forward to seeing you next week. Thank you.